Thank you very much for your interest in metacomputing. This presentation was based on the introduction of actual cases. The flow of this seminar will be a way of telling my real experiences one by one in chronological order. To me, math felt like language, paint, brush, nails and hammer. Today, many people are very interested in machine learning. Clearly, today's AI-related technologies provide a sufficiently large level of convenience. Perhaps, it would not be an exaggeration to say that almost all research fields are now using machine learning technology. At this time, we must not forget that the help of mathematics is essential to implement and utilize artificial intelligence well. This textbook was released a few days ago and was recently recommended by Professor Min-Hyung Kim, a respected mathematician. It is a textbook of about 2,000 pages. Professor Jun Ha, who recently received the Fields Medal, said that every attempt is important. Mathematics allows any definition that is not contradictory. The creative process itself, which was the writing of Professor Ha's poetry, can be seen as an important essence of mathematics. However, according to Professor Roger Penrose, who is the Nobel Prize winner in physics in 2020, even many physicists don't seem to be able to do that. Physicists, for example, want to forcefully impose a one-to-one correspondence between theory and experiment. However, mathematically this is obviously impossible. The circle in mathematics and the circle we draw on the ground in the actual world can never be the same. Based on mathematics, the set of representable objects in Plato's world of ideas can include the set of phenomena represented and appearing in our actual world, but the reverse is apparently impossible. In this regard, physicists need to take a more serious look at the uncertainty principle as well. Is the Schrödinger equation just an empirical equation? Isn't there any counterexample for that? How are particles defined mathematically? As one famous theoretical physicist put it, are particles kind of just irreducible representation? Or, is it just up to us to define? According to Professor Roger Penrose, mathematician and mathematical physicist famous for researching together with Prof. Stephen Hawking, quantum physicists tend not to be very clear about quantum reality. Most of them are distinctly uncomfortable about addressing the issue of reality at all. As seen in this slide, he said it makes no sense to deny reality altogether in this way. You may want to read his book The Road to Reality for more detail. In the Professor Roger Penrose's book, as is seen here, some people have difficulties with accepting Plato's mathematical world as being in any sense real, and would gain no comfort from a view that physical reality itself is constructed merely from abstract notions. And he also said, we should certainly take Plato's world as providing a kind of reality to mathematical notions. Having tried to argue forcefully for this matter in this book, some scholars definitely seem to have found their ultimate reality to have its home within that entirely abstract world. Moreover, he also pointed out the fact that many physicists seem hard to have a purely mathematical standpoint as they lean towards saying the real numbers seem natural. That's not true in mathematics. I will shortly point out this issue later just a little bit more. This is very famous theorem proved by Gauss a few hundred years ago. The fundamental theorem of algebra, FTA, had been considered sort of Riemann hypothesis before his proof. Although the importance of this theorem cannot be more emphasized in the whole scientific fields, it is surprising that the Gaussian FTA is not well explained in textbooks outside the field of mathematics. Had it not been so, there would have been much less number of physicists saying the set of complex numbers is nothing but just a tool of calculation. In fact, without FTA, it is hardly possible to systematize almost every kind of theory for science and engineering. Have you ever seen such a theory that never needs any kind of algebra? Every theory on which algebra is based even just a very little is never be able to escape from the Gaussian FTA. The fundamental theorem of algebra, FTA, is very beautiful in that the complex number field, we often simply call it set of complex numbers, is algebraically closed, whereas the set of natural numbers is non-algebraically closed. We can very easily be aware of the fact here by just additionally considering the elementary operation, minus. In this context, once we start dealing with any kind of algebraic method, it is finally unable to escape from the Gaussian world dominated under FTA as above. With FTA in mind, we would feel it comfortable to deal with physics and to accept many theoretic divergence problems requiring renormalization techniques based on analytic continuation in complex analysis. The continuation result is mathematically unique. Now considering a non-local property of a particle in Newtonian physics, it directly gives rise to taking account of eigenvalue problems. Here, we will soon see that Schrödinger equation could appear in a simple theoretical logic. Based on high school physics, it is necessary to consider a particle to have wave properties. To specify a physical quantity for a non-local being with respect to a local variable, the wave mechanical expression should be contracted so as to have a specified physical quantity. Mainly, we consider the case that the imaginary part is zero. Thus, we can use the following kind of interpretation. Greek letter psi, wave function including wave mechanical properties of a physical particle. As we can see here, obtaining proper wave functions is nothing but solving for eigenvalue equations. Solving for an eigenvalue equation is equivalent to obtaining the zeros of the corresponding polynomial equation. Getting slightly back to a little middle school algebra, we may remember the mathematical fact that the above zeros are actually corresponding to the conditions when the relevant linear system of equations having infinite solutions, related to coherent states. Notice that without FTA, it is even impossible to safely define such equations and solutions. Without accepting the complex numbers, there would be no algebraic exception handling. For reference, when programming a software, exception handling is significantly important. Here, note an example in which a quantum physical equation appears based on Einstein's theories and Gauss FTA from the energy conservation relation in middle school and high school physics textbooks. Also, according to the definition of the Einstein's wave 4 vector, electromagnetic wave function having the Einstein's photon energy below is defined as in this slide with no amplitude constant. For fun, we might as well challenge managing nonlinearities inherent in general relativity to derive quantum mechanical equations in almost the same way analogically. If you want to try that, you must face with managing nonlinearity problems, which are in general very tricky. Note that this wave mechanical relation still holds for a photon-like case of the rest mass almost equal to zero. The energy and the corresponding wave function are the expectation value defined above including the eigenvalue related definition and the corresponding eigenfunction. The Gauss FTA actually guarantees the existence of the corresponding linear operator with the pair of E and Greek letter psi as well. Here, note first that the use of linear wave mechanics is premised as is in the Maxwell's equations. Second, note that contradictory results would appear if we regarded the above product operator as a nonlinear function. Also, notice that the linear operator above exists for any pair of E and Greek letter psi as above where E is an expectation value corresponding to the physical state Greek letter psi. For reference, every operator is a function, whereas a function could be an operator or not. Considering all of them, we can say that FTA is actually the most important element in quantum mechanics, as FTA guarantees to have all the quantum mechanical operators in this case. The Schrödinger's equation could appear without imposing at the very beginning the famous commutation relation for the x and p here. The necessity of the imposing actually means Schrödinger equation is nothing but just a sort of experimental equation. As seen here, the above non-commutative relation could appear as a result without the axiom-like imposing. In this regard, we may as well make the meaning of uncertainty principle clearer for better understanding quantum physics. For reference, we in general deal with the case when the imaginary part of E is zero, along with Greek letter psi, a wave mechanically coherent state, which is mathematically expressed as an eigenfunction with its corresponding eigenvalue. For that, we call it observable, but we are already aware of such a mathematical structure above with some middle school algebra. For any pair of E and Greek letter psi above with the imaginary part of E being 0, the above linear operator is mathematically self-adjoint or Hermitian if the target physical system is expressed as a finite-dimensional linear algebraic problem. Have you ever thought of that? The Plato's idea versus real phenomena, theory versus experiment, simulation and thoughts versus simulation and reality by computer, etc. What is time? Is time continuous variable in nature? Or is it just up to us defining what it is as needed? As Professor Roger Penrose said, can a wrong theory be experimentally refuted? Let us define L equals 0 case and L equals 1 case as follows. Here, L equals 0 case is kind of Plato's idea covering L equals 1 case as well. We may be able to understand of what it is meant by the above L equals 0. 1 case is thinking that the following green horse like any kinds of horses could infinitely be created in the world of ideas. Notice that L equals 1 case includes a sort of hidden variables related to operators' time series properties. What L equals 0 case include are just purely mathematical non-commutative relations and no relation to actual time variables. Such non-commutative relations also exist in Newtonian physics if we don't neglect any kind of effect related to observation so that we make classical error terms zero. Light or sonic measurements also touch the state of classical particles very weakly. As we have seen previously, it is not a good idea to try to completely differentiate quantum physics from classical physics, spending an amount of our energy in it. Mathematics is a science that deals with numbers, right? We need to know how numbers are defined. It's a bit embarrassing, but let's talk about a mistake that even physicists overlook. As obvious to mathematicians as it may be, physicists often don't really care that the real number 1 and the complex number 1 are different. However, physicists will say that 1 in one-dimensional space and 1, 0 in two-dimensional space are different. Oh man. We ended up recognizing a contradiction therein so easily. To say that a complex number is only a convenient tool for calculation is not very different from saying that the vector space itself is only a convenient tool for calculation. When the domain of the zeta function changes from real to complex, the real zeta function changes to the complex Riemann zeta function. It is necessary to recognize the difference between them from definition. In fact, this recognition is essential for understanding and accepting quantum physics at a mathematical level. Now let's start dealing with some math-related problems in my R&D careers. For reference, throughout this presentation I will almost be presenting my R&D experiences in chronological order, in close relation to mathematics. First of all, I tried to look at the non-trivial zeros of the Riemann zeta function in view of mathematical physics. The analytic continuation of the Riemann zeta function expressed with a Dirichlet eta function is here expressed in terms of the Legendre polynomials, which often appear in electrodynamics. I wrote down almost all of them here, but I'll leave the more detailed calculation process to an exercise. I restricted the domain to non-trivial zeros of the Riemann zeta function. Now, this function has become nothing but a zero constant function. Then, in the same domain, integrate both sides from -1 to 1. I wrote about why integration is possible, but I won't go into more detail in this talk. The integral result must be equal to 0, on both the left and right sides. As we can see here, by reduction to the absurd without any mathematical leap error, the Riemann hypothesis can be maintained correct. Although technically I'm not a mathematics PhD holder, I hope I'm not so wrong here of course. It was a short-term trial by a freshman graduate student, me. In fact, I did not manage the Riemann zeta function for a long time in graduate school. In dealing with the physical system represented by quantum field theory, we are always faced with problems caused by the curse of dimensionality. In particular, the more accurate it is to obtain a numerical solution of a model representing a certain physical system, the more so. Somewhat roughly speaking, in theoretical physics, such a dimension is reduced as much as the orders of the symmetry groups that are enough to represent our target physical system. I rephrased the problem so that groups can be viewed in terms of the language of algebraic graph theory. Didn't I mention before that math is like a brush and paint? I would say I used a slightly larger brush to paint the exact same picture, and I succeeded it. Maybe it's because the brush was created with graph theory, so the brush I felt was moderately larger to draw the same picture much faster and at the level of the order of magnitude. Even so, not every picture can be perfectly drawn with that brush. We are not Harry Potter. We can't even use magic. Nothing is free in the world. When comparing what I mentioned before to a picture, doesn't it seem pretty natural? In fact, fortunately, many real-world problems involve symmetry, even in its approximate form. The above example can be further reduced as a problem of finding an approximate solution as shown in this slide, and here we can make use of machine learning, and so on. For reference, I think some of you might want to know about data sparse approximation and tensor network, which started to become more popular worldwide around 2011. I entered graduate school, so I will just leave here 2 pages of some relevant contents. For a major part of the theoretical contents, I referred to Matrix Computation's 4th edition and Professor Roman Oris and Ulrich Skolwak's materials. While working as a postdoc for 18 months, an internal recommendation in Samsung Display through my acquaintance had me started working on machine learning related R&D there for about 3 years. The main reason I moved to the industry was just to make a living since it was the most important matter. Money talks again. Now let's talk a little about new technologies I developed in company. Confidentiality will not be addressed in this talk. The key here was math again. In company, I developed AI related technologies in my own style. When I was at the company, it was clear to me that useful technology was not being released even in the form of a patent. I experienced it directly, so I am completely sure for that. Game theory also says so, right? We must avoid falling into the trap of SOTA. SOTA as we know it may not be SOTA. In our actual world, there are many chances that someone is secretly using certain technologies which has not publicly been exposed. The principle is simple. Again, money talks. Game theory smiles. So, I would like to deliver that we should not be accustomed to living inside the boundaries of SOTA. We can immediately Google many SOTAs, but the real Google's up-to-date SOTA may not simply be Googled. Even Samsung's confidential technologies cannot be Googled. That is the truth. We should not limit ourselves. With mathematics, we can represent and use whatever we can practically abstractly imagine. Mathematics is the most fundamental language that makes it possible to understand problems well, represent them properly, and create and/or utilize optimal tools we can use. Mathematics is clearly important even in implementing and utilizing artificial intelligence at a high-end level, of course. This is about the work I did at the company I stayed for a few months before starting up Metacomputing. When I entered the company, I had about 2 months left before the deadlines for the final reports on the results of a few national projects worth about 5 billion won overall, and the problems the company was dealing with were perceived as very tricky types of problems. At that time, the company had been consigning advising professors in AI related fields for the relevant tasks which were to be passed to me on October and November 2021. What I felt was that several professors, including the professors responsible for evaluating the level of the achievement of the company's AI technology implementations, seemed to be trapped in some preconceived notions. Of course, It may have been because they were busy, but most of the time, based on the already published SOTA papers, the professors tended to say something like it's not achievable. Actually, that was found to be false. The AI-related technologies introduced in this slide are characterized by including geometry, algebra, theoretical physics, and industrial engineering elements altogether. Do you remember when you were in school and were solving math problems? With a pencil you drew lines, x and y axes, intersecting straight lines, and tried to draw angles between them. When dealing with our real-world problems, the first thing we should do is not to look for answers or search papers first, but to define the problem ourselves and think deeply about the solutions first. Even after that, it will not be too late to search for the papers. On the contrary, there are many cases where a student reading answer sheets and explanations first tends to have his or her math skills and grades dropped. I hope that students can do training enough to shape phenomena mathematically from an early age. I would say it's like drawing at will. For instance, it would involve the process of properly setting the boundaries seen in phenomena, the process of defining different objects through this process, and the process of creating mathematical relationships and equations between them, etc. From now on to the next 20 pages perhaps, we may as well try being relaxed, feeling ease. Don't worry about the number of pages since just simple things are going to be addressed, so we'll get to that quickly. Naming is so important in math as well, right? Even when we use a single symbol, we are very attentive and often sensitive. Even when we name various kinds of names in our daily lives, therein we can see boundaries and relationships, and they are all mathematically representable. Have you ever visited library to borrow a book? When we don't know the title of a book we've read a long time ago, we sometimes look for it with the help of a librarian. However, giving librarians misinformation or potentially confusing information can also make retrieval difficult. Nonetheless, we are going to see that mathematics can help minimize even these difficulties. Thanks to my friend Kevin for drawing the cartoon. What will a future library look like? Digital revolution means what? How does it affect society in the future? If we take a closer look at this, wouldn't we be able to get a clearer answer than we have been aware of it? If you look up digital in a dictionary, it is called nothing but a number. Mathematics is a science that deals with numbers. In other words, in the digital revolution era, mathematics plays the most fundamental role by definition. A library is a facility that organizes information, so information has to be represented in numbers by definition. Of course, it is also important to well represent it. From now on to the next 20 pages perhaps, we may as well try being relaxed, feeling ease. Don't worry about the number of pages since just simple things are going to be addressed, so we'll get to that quickly. Naming is so important in math as well, right? Even when we use a single symbol, we are very attentive and often sensitive. Even when we name various kinds of names in our daily lives, therein we can see boundaries and relationships, and they are all mathematically representable. So, how well can we represent that information mathematically? According to the dictionary, information is related to knowledge, and knowledge is related to object, and object is related to representation, which is related to materialization and shaping. The mathematical term irreducible representation in quantum physics actually expresses the essence of quantum. Eugene Wigner showed already in 1939 that the elementary particles are related to the irreducible representations of the Poincare algebra. This is our daily example of unrequited love, and this too can be mathematically embodied, and all the words defined in the dictionary can be mathematically shaped in the form of a digital tree like this, and the royal genealogy can also be expressed mathematically. In the process of mathematical shaping, we always demarcate the objects so that we can distinguish them from each other and define them. If we set boundaries well, our relationship will be pretty. Even when creating a single mathematical field, it is possible to neatly define the boundaries and to obtain a great deal of interesting mathematical results from it. Think about global warming for a moment. Mathematics is important to make computing smart. Reducing unnecessary computation as much as possible is directly related to a matter of greening the environment. As you can see, most of the electrical energy we use comes from fossil fuels. Imagine that in the future, as the number of global IT companies increases, it is as if new countries are added one by one on the Earth. It is well known that even a few % more carbon dioxide in the atmosphere can cause climate anomalies. This is a really important issue. Professor Junha also emphasized that it is really important to create or break down boundaries between fields that look different from each other, allowing them to freely cross those boundaries. From time to time, I said similar things to my friend, but he just made fool of me saying weird. A few months ago, he made a phone call to me saying sorry to me after watching the Professor Junha's public lecture. I think the Professor Junha's lecture was very concise. Yet it was enough to give a great deal of insight to many people. For more detailed information, you can watch it on YouTube, or you can read the English translation at Metacomputing's website. Please take a look at the chestnut problem left here when you have some spare time if you haven't seen it before. Have you heard of first principle? In physics, it is often referred to as first principles. With only the information of atomic distribution, it is possible to obtain physical information of the quantum system. The first principle is defined by the minimum number of premises and assumptions that are absolutely necessary, as in Occam's razor. And as needed, we do the same kind of tasks in the fields of mathematics and philosophy as well. Whenever doing these, we see that setting boundaries must be preceded before defining mathematical objects and giving them meanings. And only then, we can differentiate the objects and can find relationships among them. The digital revolution will broaden the scope of human thinking and perception so that we can more effectively recognize what we don't know and what we want to know. And these amazing things happen with the help of countless mathematical operations. In order to achieve a digital revolution while maintaining a green planet, we will need to be able to use the language of mathematics very flexibly. Before the end of this presentation, we will come to see that it is possible to obtain and utilize kind of data physical information formed by different English sentences, as if having performed first principles simulation in computational quantum physics. Here we are looking at a chunk of English sentences like a sort of physical particle. Here, let's remind ourselves of the middle school problem regarding sound. I believe many people have an experience of carrying out this experiment in science class. The resonance cases provide kind of good sound, while we hear somewhat strange sound otherwise. Apparently, we hear something strange even in the non-resonance cases. Mathematically, a resonance case corresponds to a solution to an eigenvalue equation. as we set eigenvalue equations to find out such resonance or coherent states by solving for the equations. We may also try setting some kind of equations dealing with the opposite cases, we may say non-eigenstates. Of course, in quantum physics, solving for eigenproblems is very important. However, this does not imply that there is no system other than systems described as eigenproblems. In a pure mathematical standpoint, we don't have to stick to a concept of being existence which is experimentally observable and is expressed as an eigenstate. As the Nobel Prize winner in Physics 2020, as Professor Roger Penrose emphasized, to me also, it makes no sense to deny reality altogether in this way. Indeed, there are a number of physical studies on such non-coherent states. So, here mathematics counts again. As we've just seen before, eigenvalues are considered importantly in physics. Coherent states are expressed as eigenstates. The nature of an eigenstate is from conservation invariant symmetry. Just simply you might think they are the same. No problem. Going further mathematically, automorphic forms nature can be said also from conservation invariant symmetry. So, it is natural to think that they should be related mathematically. Yes, the discrete beings, eigenvalues, are mathematically related to the continuous beings, or automorphic forms, which are continuous functions. In fact, we have already learned some very simple automorphic forms in middle school. Roughly saying, an automorphic form is a function becomes the same form of function when we feed a dividable variable in the function. Then, we may now remind of a number of such functions we learned when we were young. From now on, let's just focus on the existence of relations in between automorphic forms and eigenvalues. To see a great relationship between physics and mathematics, we would be better off considering Langland's program in mathematics a little bit, which is kind of study on grand unified field theory in math. Let's begin with the bottom-up construction of the complex number field. As for this construction and intriguing prime numbers inherent in it, I recommend you to find very concise lecture notes of Professor Min Hyung Kim online. You can just Google him and visit his website to obtain the notes and relevant materials. As for the prime number generation I calculated out in an approximate way, you must find interesting inside it showing the power of mathematics. Here we can be more sure that this very important mathematical fact really holds in real calculation. Note that all of the n are prime numbers. Isn't that interesting? Anyway, the point is that we will see that this kind of automorphic form f is related to Frobenius eigenvalue in the Fermat's last theorem and Langland's conjecture in connection with Artinel function, the analytic continuation of which defines the grand Riemann hypothesis, which is related to the distribution of prime numbers. In the next two slides, you will find crossing over boundaries in mathematics in relation to the Langland's program, the fundamental lemma of which the proof made a field medalist 2010. In the proof, the classical physics is related via algebraic geometry. Evidently, there are theoretical relationships in between physics and mathematics. Therein sort of irreducible objects play a key role. Crossing over boundaries is also emphasized in the Professor Junha's recent public lecture. In his lecture, he talked about that in relation to his research in Korean, translated into English here. For the full English translation, visit Metacomputing's website. As seen here, everything is interconnected with each other in language of mathematics. Even machine learning needs a Langland's program as is described in the right figure. Finally, we have come to the slide where we begin to introduce our company. There were some great adversities at the beginning of our business. Of course, we've grown as well. As soon as we started up Metacomputing, we ran into barriers, something like how much sales we have achieved. In academia, it's like barriers such as how many papers we have written. In school, it's like a stigma related to something like math grades. For us, it was too difficult to make the first sale. Fortunately, the quality of the first sale can be evaluated to be at a high level. It is related to a national R&D policy studies. Although the amount is not large, it can be said that Metacomputing is now beginning a very important job after a great achievement in a short period of time. It can simply be checked by considering the size of the budget that has been invested in existing related national projects, tasks and their resultant reports. Even so, when we do document evaluation, it is always filtered out by indicators such as sales level, so we have to pay attention to sales as well. Metacomputing started its actual business from February 2022, according to the records for the tax invoices. It became a member of the Metaverse Alliance and soon became research institutes recognized by our national institutions. We had a neat idea about Metaverse, so we applied for a related national project. However, as we were aware of the fact that our company had no sales, we tried to form a great consortium that included powerful IT facilities devices with famous scholars, professors in related departments fields. We experienced a hardship here. As soon as we started the business, it was the business support that we invested the most time in. As it was the world's first innovative idea to our best knowledge, I was sure that it would be something the Korean government would love. Not only did our proposal for the Prosumer platform service operate under a well-defined mathematical system and under a systematized sharing economy type underlying infrastructure for supercomputing, but also our great consortium already had metaverse specialized facilities including supercomputers, XRI tracking labs, and so on. Furthermore, our manpower was amount of about 20 men per year at the level of PhD professors just for 1 billion won. So, I thought that it was almost like volunteering. However, the reality was not so. We were immediately rejected in the document evaluation, saying our KP setting and commercialization plan were insufficient. Before then, we were very sure that our proposal is very innovative and providing managing new concept drilling into the essence of the quantification of the usefulness and mathematics-based ethics for metaverse, perfectly fit with the project's requirements. This was the first time when we were aware of the truth. The reality can be deviated a lot from our thoughts and predictions. The reality was that there was no chance to be interviewed with the idea we had thought very neat, even if we had already been seen almost impossible to pass through the final evaluation. In comparison to RAPA, fortunately, Korea Technology Finance Corporation well evaluated our ideas. As soon as we started our business, we got the Innovation Growth Type Venture Business Certification. A total of 4 patent office applications were filed until April, but we've experienced another hardship. From April this year, we came to proceed a free POC for about 1 month on the premise of the practical contract for the project related to the POC. But due to differences between Metacomputing and the customer company on the scope of the POC requirements, it was extended to about 3 months. In the middle, there was an internal opinion that we should just do it with another company since it is we that have the core technologies for that. But the doctoral director of the company who was in charge of insurance related affairs was a good person, so I was able to be patient since I trusted her. By solving all the missions presented in the POC, the process for the contract began. However, due to the situation that the company's business director responsible for the project was changed, the ongoing contract process came to be stopped. Then, I was told that we have no choice but to comply with the demands of the new business director since the person in charge is now different from the past's. Considering the ease of proceeding the project further properly, we had to decide to temporarily suspend this project until the situation at our company improves or we find another better partner in the future. Not long after that, the company went public on the Korean Stock Exchange and went up to its ceiling price immediately. Well, according to some newspapers, it seemed like as if our core technologies or their alternatives had successfully been prepared for normally proceeding the project. Probably, beyond the scope of our patent claims, The budget may be higher than expected to succeed the project. Still, we are interested in this project as well as applied for a related patent in the same context. So if we can afford it in the near future by ourselves, we would like to put some input into it on our own. The story about our hardships seems to have ended here. After that, our metaverse ideas started to be re-examined by the NRF, and in-depth reports on quantum physics and computing that added a bit of fresh perspective also got attention greatly. First of all, our social media pages have been getting noticed greatly. The number of followers on LinkedIn is reaching the level of 3,000, and one of our Instagram feeds got 1.5 million likes that are comparable to BTS getting likes. Surprisingly, since then, I have been invited as a seminar speaker by national organizations. It is my great honor. Not long ago, the first sale I mentioned earlier was achieved by the recent acceptance of the NRF Policy Research Service project. Also, Metacomputing was recently issued a full guarantee of 100 million won from Korea Technology Finance Corporation. Not only did we get the full guarantee, but also we got the maximum 100 million won. This actually corresponds to a small startup business like us for the first application. Thankfully, even though our sales were not kind of great, I think there were many grateful people who have positively seen us. Now, let me introduce a little about patents. Broadly speaking, we are in the process of applying for intellectual property rights that are of great public interest. First of all, this is an example of a device that allows you to make use of a landline phone with, as we imagine. It has a characteristic that can clearly quantify the level of the patent's economic ripple effect. Secondly, this is about the metaverse we talked about earlier. For more details, please refer to the October issue of NRF Webzine in the relevant in-depth report. The point is that here, mathematics is used as if it were a language and were an art tool. Market is requiring metaverse's usefulness quantification. Let's make a comparison between a task for creating a blueprint and a task for decoding a password inherent in the universe. The former task will be highly likely to be much easier, right? We have a good set of brushes and paints for metaverse. Leibniz's theory of possible worlds has systematically been researched since several hundred years ago. It is already known that mathematical logics can computationally be utilized well. Theory of artificial intelligence will have been getting embedded into the future metaverses mathematically. Even the utilization of quantum computing and the relevant cybersecurity issues therein should be managed at the same time in the near future. With these in mind, it is necessary for us to try revisiting the today's metaverses, pondering deeply about what future metaverses would be good and neat. Lastly, this is for accepting information from an electronic document including non-textual ones. It is closely related to the core technology for the exception of insurance term information as I mentioned before. Through the language mathematics, it is possible to make and cross over boundaries and to define objects and make relationships between them. Such works are actually nothing but countless works of art, right? We will be able to feel the greatness of mathematics not merely in industry but also anywhere in the universe. Thanks to mathematics, I would be able to say that we can systematize whatever we can imagine. We have now reached almost the end of the seminar. A single abstract can be treated as if it were an individual particle. A patent application for this technology will be filed soon, and related NRF reports are planned to be published in the near future. The reason we can successfully carry out this NRF policy research project is that the related proof of concept, POC, has already been made. In other words, the validity of our methodology has been tested verified. It would be difficult to go into great detail on this matter, but the main idea itself is simple. We can create all English sentences with alphabets. It's not very helpful. We can systematically obtain a much greater number of chunks like those alphabets. there would be the supremum of the number even if the number can increase to some extent. I feel like such a chunk is a sort of an irreducible representation. This can be of great help. It may contain very important information in a set of information. Such information may be shown in very different forms. However, we often experience that it is not easy to predict what kind of information it actually contains and in what form it may have. In times like this probably, the simpler and easier it is to go, we can well define such blocks in advance, so that we can properly utilize them. And if we refer to various systematic theories that already exist in order to make use of them for assembling, we often get interesting results. Since such an assembly is done by the computer, we don't have to worry about that too much. Metacomputing has been doing these things recently, and I'm proud to say that we're doing something socially very important. In the next few slides, we can see the characteristics of the awarded projects of NSF through a set of post-processes. Through this, we can learn a great deal of information that we did not know. There are hierarchical and entangled relationships. There is something like a relationship map as if it included many complex connections between countless stars that we had seen briefly before. Our government has been conducting researches for the purpose of discovering promising technologies in the future, and as is known, it is not far away from machine learning based methods. We are really glad that metacomputing can help people escape from such kind of mold. Although we plan to apply for a patent soon for that, we have basically set as one of our business principles to fulfill our social responsibilities so that our technology can be used well for the public good. As seen here, we could try to make the library of the future a hub of digital resources, or connect the digital resources with the metaverse ecosystem suggested by metacomputing, making it the central point of the great virtual world, while trying not to deviate from the dictionary meaning of the library. For reference, a library has a dictionary definition of a place where resources are available to use, borrow, lend, etc. The future library, where digital resources are freely stored and utilized, will greatly contribute to the strengthening of national power as it has in past history. The stories I'm talking about can feasibly be achieved if they are implemented by properly combining existing technologies well. Mathematics cannot be omitted here, of course. No matter how good the materials are, they cannot be connected to each other well, and mathematics serves as a bridge that makes this possible. This talk ends here. Before that, we listen to what Goethe and Gauss said. Whatever you can do or dream you can, begin it. Boldness has genius, power, and magic in it. Begin it now. Mathematics is the queen of sciences and number theory is the queen of mathematics. She often condescends to render service to astronomy and other natural sciences, but in all relations she is entitled to the first rank. This is the end of my presentation. Thank you for listening to our long story.